All right. Good morning, everybody. Let's continue. Here's the plan for today. 10 out of 10. All right. Everybody ready? Let's settle down, please. All right. Let's. All right. So here's what we're going to do today. We're going to continue with chapter 20. We started it last time, but we're going to pretty much start again, almost. We're going to take quiz number 2. Here's a question for you. It's a conceptual question. Here's a conceptual question. Suppose I mix ice and water. Right? Ice at a certain temperature and water at a certain temperature. So water means it's above probably 0 degrees, right? And ice at some negative temperature, below 0. So here's the, I mix them, so I get this. The ice starts somewhere here. And it will, the temperature rises. This is the ice. And then the water, the temperature will start to drop, right? So again, what am I doing? I mix ice with water. The temperature of the ice will rise, the temperature of the water will drop, and this is as time goes on. So here's what happens. The ice will do this, and then it will flatten, and then the water will eventually get there. And the question is, all right, so this is the water's temperature, and this is the ice's temperature, and this graph is not to scale, of course. So this is some negative temperature. Maybe the time axis, I could have centered it somewhere. But the first question is, what's the equilibrium temperature of all of these together? What's the final temperature of the mixture? 0. 0? Yeah. If you say 0, I need to get convinced. Or it actually is 0. And the question is why? Yeah.
The change in heat. Exchange in heat.
So the ice warms up. The question is, why is the temperature here? Why is that 0 degrees Celsius?
Because the ice cools the water.
It's changing state.
It is changing state. So, okay, so this is ice until it changes state. Let me hear from one more person, and then I will.
Because the curve for the ice flattens out at 0 degrees.
When it changes state also, yeah?
It's because the temperature will like stay constant until all the ice is melted into water. So that's why it stays flat.
Good.
For that amount of time.
Excellent, yes. Okay. So what you said is correct, yeah. So the ice temperature will rise until it starts to melt. When it starts to melt, you add heat, but the temperature doesn't rise. The heat will go into melting the ice. So at this point here, the ice, this is the temperature is 0, and the ice starts to melt, right? How about the water? It's still water above 0, right? And then the temperature keeps dropping until it becomes water at what temperature? At this point, it becomes water at 0, and then it continues. Right. So the final temperature is actually 0. Yeah. Let's see. Yeah, I think that's all I wanted to say. All right. So let's continue with what we did last time. I think we talked about the mean free path. So you have a gas in a box, and you would like to know how far does a gas molecule go before colliding with another molecule, right? That was the mean free path. And we ended with the following formula. I'm going to just write it down. the mean free path. So in fact, I'm going to erase this now because it's not. Yeah. Can I erase here? Okay. So we did the mean free path. So if you have a gas in a box, how far does it go before colliding? And that mean free path was called lambda. And it had this lengthy formula kind of, it was 1 over some constant, n over v. V is the volume of the molecule, the volume of the box, the volume that the gas occupies, and capital N is the number of molecules of gas within that box, right? Within that volume. And then R, or R squared is the radius of the molecule, of the gas molecule, right? If the gas molecules are too big, then they will collide more frequently, right? They're larger, they have a larger radius, then they will collide too frequently. If they collide too frequently, it means they will move less before they collide, right? Okay, so we did that, and we were asked what was the mean free path for a nitrogen molecule. We also did that question. So let's do it again because it has been a while. So let's say you have a nitrogen, nitrogen gas at T 20 degrees Celsius, right? And T is equal to one atmosphere. So atmosphere. So suppose you have nitrogen gas at that, and then at 20 degrees Celsius, and the question is find lambda. So find this mean, the mean free path, and they tell you that the radius of a nitrogen molecule. So the radius for N2 is about 10 to the minus 10. 10 to the minus 10. Yeah. So what should I do? Should we find lambda? I know the radius. If I knew what N over V is, I would just substitute, right? So let's see what we know and what we don't. So 1 over, I know what 4 is. I know the square root of 2. Then plug it into the calculator. Pi. And then this N over V, we need to figure what it is. And then R squared. R is 10 to the minus 10, so like this, right? So if I knew what N over V is, I can find this. So how is N over V related to this pressure and temperature? Is there a formula that, yeah?
Ideal gas law.
Ideal gas law, yeah. So if you use the ideal gas law, you know that PV equals to, I can use little nRT, the number of moles times R times T, but I want the number of molecules, right? Capital N. So I will use this form. Capital N KB times T, right? And this KB is the
Boltzmann constant.
yeah, Boltzmann 1.38 times 10 to the minus 23, right? So I want N over V. So if I divide both sides by N, by V, and then divide both sides by KB T, so I get P over KB times T is equal to N over V, isn't it? So if I find this, it is equal to N over V. So that's what I need to do. So plug in the pressure, KB and T, so let's do it. So N over V is equal to the pressure, KB times T. The pressure is 1 atmosphere, but 1 atmosphere are not good units. I want pascals. So 1.013 times 10 to the fifth. KB is 1.38 times 10 to the minus 23. The temperature should be in is it 20 degrees Celsius? Should I put 20 or should I put something else?
293.
293. Add that 273. Good. 3. You will get about 2.5 times 10 to the fifth. Times 10 to the 25th, sorry. Per cubic meter. So, per cubic meter. That's the number of molecules per cubic meter. Yeah. It should be a lot, right? Yeah. So, then we plug this number here. It's 2.5 times 10 to the 25th. 2.5 times 10 to the 25th. Okay, so if you do that, you get about 2.3 times 10 to the minus 7. Okay. All right, so that was that. And so here's a conceptual question. Suppose the temperature, you put oxygen in a container. So here's oxygen in a container. And the container is rigid, meaning if it's rigid, does it mean, can the volume of the container change? No, it's rigid. The volume doesn't change, at least not easily. So there's oxygen in this rigid container. Suppose I lower the temperature. The temperature is lowered from, let's say, 300 Celsius to 0 degrees Celsius. Does the mean free path change or stay the same? So does lambda change or stay the same if the temperature is lowered?
It'll increase.
I've heard it doesn't change?
It'll increase.
It'll increase
And
because
I
the
heard
temperature
increase.
is bigger, so N over V is gonna be a bigger number.
Okay.
Oh, but we divide it though.
It's gonna be smaller, and then a smaller over
Oh, that's
1 is bigger.
So just to be sure,
I mean, 1 over
the temperature goes from 300, right, degrees Celsius to 0 degrees Celsius. So that's the, so I heard bigger, I heard smaller. Does anybody say stay the same?
No, it's
Smaller. Okay. Well, let's think about it. So when you cool molecules down, does the R change? No. No. Okay. So the only thing that can possibly change is the number of molecules per unit volume. So is the volume changing?
No.
No.
Oh.
Is the number of molecules in the box changing?
No.
No. So it stays constant.
Oh.
Oh, yes,
Yeah. So it stays the same. Yes.
How does that correlate with the temperature? Like, because N over V is equal to P over K sub BT.
Yeah.
So if we increase the temperature, does it just kind of compensate it somewhere else?
Yeah. So if the temperature decreases, the pressure will also decrease. And
Oh.
that ratio will just stay.
The ratios. Okay, thank you. That makes sense.
Yeah.
Oh, that's tricky.
It's a tricky question, right?
Yeah.
Yeah.
Totally understand.
Okay, so let's go to the pressure now in a gas. I'm going to do it slightly different than the book. I think it's simpler this way. You can read the book for it. So the idea is this, so pressure. So again, I will go to my gas, and I'm going to assume you can assume any shape, but we'll take the nicest shape or the easiest shape to work with. And that shape would be a box. A box that is, in fact, not even more specific, a cube. It would be a cube of length L, of side L. So here is a cube of side L. It's L by L by L, right? L, L, and L. L on each side. Okay? And there are molecules inside in this box. N of them, right? and molecules in this box. So what's the volume of the box first of all? Let me put, because we'll have velocity also, it has the symbol V. So I'm going to distinguish, so volume will be given like this. I'll put little 2 bars to just distinguish it from velocity. So what's the volume of the box?
L cube.
Huh?
L cube.
L cubed, yeah. L cubed. It's L by L by L. Good. All right. We want to understand pressure. We're going to remember we said there is a velocity distribution. There is some gas molecules will be moving fast, some will be moving slow, but they would have some average some average velocity, and we will talk about that average in a little bit. And if you're in my class that we'll meet tomorrow, we will go over that in more detail. We'll talk about V average and the average of V squared, and then the most probable velocity. If you were in yesterday's class, we already did that. So we're going to go over that. So, so the gas molecules are moving around, and every time they hit the side of the container, they bounce back. We're going to assume it's an elastic collision, meaning it bounces back with the same speed it impacted the container. So here, let's just look at this side of the container. I'll just look at the side view. So let's take a gas molecule that's moving this way. Just one molecule for now. Think about one molecule. It has a mass m, and it's moving at speed v. Okay? It will hit the side and then bounce back, right? It will bounce back. Okay. This is forward, and then it bounces back. And it will bounce back with the same speed v. And then what it will do is we'll go back and hit this side, and then go back and hit this side, and back again. We're just going to assume it's going back and forth. It's horizontal. Okay? And this will do the job, actually, will give us the right result. Does that make sense? All right. So, what is the momentum, P initial? P, momentum has the symbol P also. Like pressure. What should I do? Momentum, yeah. Momentum. So, P initial. What is the initial momentum?
M times V.
MV, yeah, MV to the right. MV. And then P final. Negative MV. It's negative MV. So the change in momentum, delta P, is equal to what?
0.
Well, it's
Negative
minus
2.
minus. You will have a,
Oh, so -2?
yeah, it would be negative 2 MV, right? You would have, the final is negative MV. Assume the right is positive, for example. So the left would be negative. So you have negative MV, that's the final, minus the initial, which is positive MV. So you would have negative twice MV. Negative twice MV. And negative twice, all right? That's the moment. Now, suppose this molecule hits the wall. How long do I have to wait for it to hit the wall again? Or in other words, let's say it just hit the wall. What does the molecule have to do in order to hit the wall, that same wall again?
Control L distance.
Yeah, so it just hit the wall, so it has to go back all the way to this wall, and then back again. So it will travel 2L. Yeah, right? It just hit the wall. It has to bounce back, hit this wall, and then come back to this wall. So it has to travel a distance 2L. If it travels a distance 2L, what's the time? What is the, remember the speed, V is the distance over time.
2L over V.
So, yeah, so the time, let's call it delta T, will be distance over speed. So it's 2L over V. 2L over V. That's the time. Now I want to know how much force does it apply on the wall, or how much force the wall applies on it. They're the same in magnitude. So what's the relationship between force and momentum? Force is what? Come on, get the second one.
F equals MA.
F equal to ma. And in terms of momentum,
Derivative of momentum.
dp dt.
Oh my god.
Yeah, dp dt. Or the change in momentum over time, right? On average, it's about delta p over delta t, right? Delta p over delta t. Change in momentum over time. And by the way, I want just the absolute value of the force. I just want the magnitude of the force. I don't care about the negative signs now. So, so the magnitude of the force would be this, delta P is this negative 2 mv, but I don't care about the minus sign anymore. So 2 mv divided by delta T, which is 2L over V, and so I get mv squared over L. That's the force. Is that the force of all the molecules or just one of them? One of them. Right? This is just by one molecule. In a little bit, I'm going to get the force for the entire thing, and then we will get the pressure. Okay? So that's the force from one molecule. So what's the average force from all the molecules? Yeah. Delivered on one of the walls. How do I get it? If you have the force of one molecule, how do you get the force from 10 molecules?
Multiply by 10.
Multiply by 10, yeah. So the question is this. I'm assuming that I have molecules just moving horizontally. But is there anything more favorable about the horizontal distance this way, or the motion this way, or this way? There are three axes, right? The x-axis, the y-axis, and the z-axis, right? The molecules could be, they could be bouncing between these two walls. They could be bouncing between this front wall and that back wall, or the top and the bottom of the box. So on average, how many molecules do you think would be moving left and right versus front and back and up and down?
Third.
A third of them, yeah, yeah, because all of the, yes, I don't know who said the third, but you're right, because there is nothing favorable about this direction versus that to a molecule. To us, maybe we want the exit, but to air molecules, they don't, you know. So, yeah, so a third of them would be moving in this direction. So on average, to get the average force, I need to multiply by n over 3. N over 3. Yes?
Does gravity play a role now?
No, we would not worry about that. It's negative. Yeah. Yeah. Luckily, actually. Because imagine if they all settled down on the ground. What happens? You can't breathe anymore. Yeah. So that wouldn't be good. But yeah, you're right. I mean, you can have those considerations, but for now, let's just let them bounce around elastically. Yeah. Okay, so 1/3 of them are moving, and are all of them moving at this speed?
No.
No. So to get the average force, in fact, average, this is for the n over 3 molecules, right? 1/3 of the molecules that are moving this way. So you get n over 3 times this average. So that would be m over L. And then since I'm averaging the speed squared, so I'll take v squared of the first molecule plus v squared of the second molecule plus v squared of the third molecule plus v squared of the fourth and so on, and then divide by the number of molecules to get the average. So this is the average of v squared, not the average of v. The average of v squared. It's called VRMS. Yeah.
I got lost at the third.
At the 1/3?
Yeah.
Yeah. So the box has n molecules, right?
Yes.
This box has n of them. So the question was, approximately how many of them at any time will be moving left and right versus up and down versus front and back?
Yeah.
So how many do you expect on average? Do you think all of them will be moving left and right and none of them will be moving front and back? Probably not, right? Yeah, probably not. So if they're just randomly moving, on average, since I have 3 axes of motion, 1/3 of them would be moving in each direction. Yeah.
Okay. Thank you.
Yeah. Yeah. Yeah, so on average, that's what's happening. Of course, I mean, at any moment, is it exactly 1/3? Probably not. But on average, that's what it is. So I get this, and this one will be called, since I'm averaging, it will be called VRMS squared. We will do a calculation on this tomorrow, and I have one in the homework. So we will do one of those calculations. Anyways, it's just some average, some kind of an average, okay? We will learn how to calculate. So now, that's the average force. So how do I get the average pressure?
Ideal gas law.
Okay, I can do, I'm going to use the ideal gas law soon, but how do I get pressure from force?
Pressure over area?
It's the force over area, yes. Yeah, pressure. So now P for pressure. That's this section, pressure, is the force over the area. So I'll get P is, I'm going to put this for the force, this whole thing, 1/3 and, you know, all this stuff. 1/3 and V squared RMS over that. Am I missing something? Oh, I'm over L. Yeah, there is an L here. And then what's the area of the side of the box? L squared, yes. So we end up with P is equal to 1/3 N M V squared over what?
L cubed.
L cubed, yeah. L cubed. So now, okay, what is L cubed? That's the volume of the box, yes. Volume of the box. That's L cubed. Let me, so I'll get this. P is equal to 1/3 and M V squared over the volume. You see why it's, I put the bar because I have two V's now. V for volume and V for speed, right? Or maybe I should write RMS. I should keep writing RMS still. Yeah. Multiply both sides by V to make it look like the ideal gas law. So I get PV is equal to 1/3 of N times M V RMS squared. Okay? So get that. Now, what does the ideal gas law say about P times V? Am I missing something, by the way? Maybe I shouldn't be doing it from memory. Is it okay? If I miss like a factor of like 1/3 or something, I have it, I think, but okay. All right, so I'm going to relate it now to the ideal gas law. So ideal gas law says PV equals to what? It's equal to N, K, V, T. You might ask, why didn't I use nRT? Well, because I have N here. I have the number of molecules, so it's probably nice to use the other form of the ideal gas law. So first of all, why is this important, or what insight does it tell us? It tells us where the pressure comes from. It's just molecules, it's force per area, like we learned from definition. And then where does the force come from? Every little molecule bounces off and delivers a small amount of force on the wall. Or it experiences a small amount of force from the wall. Depends on how you want to look at it. And so those little forces add up. And they add up into a force per area. And that's the pressure. And now, even more importantly, it's this relationship that I'm going to modify a little. So I'm going to take these two, and I'm going to cancel N on both sides. Cancel N on both sides, so I have this. 1/3 1/3 m v squared is equal to kb times t. So what does mv squared remind you of?
Kinetic energy.
It reminds us of kinetic energy. It's only missing the half, right?
Yeah.
1/2 mv squared would be the kinetic energy. 1/2 mv squared would be the kinetic energy. And by the way, I'm going to, yeah, let me write this one. Oh, I used that word already. So I'm going to do this. I'm going to solve for VRMS just to get that out of the way. That VRMS is equal to 3 kb t over the mass square root, right? Multiply both sides by 3, divide by m, and take the square root. That's VRMS. So that's one thing. So if I say the temperature is a certain, we will do a calculation like this in a moment. But if the temperature is given, let's say today it's about 20 degrees right now. That's 293 K. And the question is, how fast are the air molecules moving on average about? Well, you take Boltzmann constant, 3 times Boltzmann constant times the temperature in Kelvin, and divide by the mass of the molecules that are here. Mostly what? Nitrogen, right? And some oxygen, yeah. And that's what will tell you the RMS. Next, I'm going to, again, use this one and figure out how the kinetic energy is related to temperature. The kinetic energy per molecule. How is it related to temperature? And it looks like this. I'm going to just copy paste. I'm going to just copy this on here. So I have 1/3 m v RMS squared equal to k b times t. That means m v RMS squared is equal to 3 k b t. Okay. Now we said mv squared reminds us of the kinetic energy. It's only missing the 1/2. So what should I do to make this into a kinetic energy?
Multiply by.
Yeah, multiply by 1/2 both sides, right? So multiply both sides by 1/2. So if I multiply the left side by 1/2, I'll get 1/2 mv squared RMS is equal to 3/2 k b t. That's the kinetic energy of one molecule. So I put the energy. Usually they put epsilon for kinetic energy, and they put translational. This is because it's moving. It's translated, moving from one spot to another. This is the kinetic energy. Of one molecule. So that kinetic energy is 3/2 k b. Okay. So each molecule would have this much kinetic energy. So just based on the temperature, you would have that much kinetic energy. Now, what's the lowest temperature you can have, or what's the lowest kinetic energy you can have? Huh? 0. Yeah. The lowest would be, you can't have negative, right? Because the mass is a real number, it's a positive number. And the speed is a real number. When you square it, you should get a positive number, right? So this should always be non-negative. The lowest you can have is 0, and that happens at t equal to 0. Okay? So that's one thing. Now, how about if I want the kinetic energy of all the molecules put together? What's the total kinetic energy, which we will call thermal energy? The total energy, which we call E thermal. In the last chapter, we were only able to calculate the change in E thermal. But now we will know E thermal itself. How much is it? Not just its change. Looks like this. what do I do? If this is from one molecule, what do I have to do to get all the molecules?
Multiply by 6.0.
If I have one mole, I will multiply by Avogadro's number. And what if I have, yeah, by the number of molecules, which is n. Multiply by the number of molecules, which is n. So if you multiply this by n, you will get 3/2 n kb times t, or n kb is the same as nr. So this is the same as 3/2 n r t. Have we seen this formula before? Yeah. We have seen it as delta E thermal is equal to 3/2 nr delta T. Right? 3/2 delta T. And by the way, what kind of gas have we assumed here? Monatomic or diatomic?
Diatomic.
Diatomic.
We assume, so if you say diatomic, where exactly? And if you say monatomic, how do you know?
Formula.
The formula?
Yeah.
So, oh yeah, this one is for monatomic, yes. Yeah, we got this for a monatomic gas. We had the 3/2. You're right. And the assumption is, if you had the diatomic, it will not just translate, which we will encounter in a moment. It can also rotate about its own axis. It's like two balls and then attached by a spring or a stick. They could rotate about two axes, or they could also vibrate. That's also a possibility. So for a diatomic, it will be a different number because of what's called degrees of freedom. So yeah, well, let's discuss it while we're at it. Degrees of freedom. What do you think a degree of freedom means? I can't tell. Oh yeah.
Is it like a plus or minus of like how much area question mark the molecule has when it's in the
Okay. The freedom, how many directions it's free to kind of move, basically. So if it's a ball, first of all, if a ball rotates by itself, it doesn't look different, it's the same. So for a single atom, if you flip it around, it just looks exactly the same. That doesn't count. So it can have translational kinetic energy. It can move in the x direction, it can move in the y direction, and it can move in the z direction. So 3 degrees of freedom if it's monatomic. And those 3, that's where the 3 comes from. Each degree of freedom is worth a 1/2 kT, a 1/2 kT. 3 of them, they're worth 3/2. For a diatomic molecule, it can move in all 3 directions, so that's 3 degrees of freedom. In addition to that, it can rotate, and it can rotate about another axis, or it can rotate about its own axis. This one doesn't count, it looks exactly the same. So those, about this axis and this axis, that's an additional 2 degrees of freedom. So 2 plus 3 will be 5, so you'll get the 5/2. There is also the vibrational degree of freedom, but usually for ordinary temperatures, from 100K to about a few thousand, those vibrational are insignificant. Unless you go to like 5,000, 10,000 K, then you have an additional 2 degrees of freedom, then you have